Hello, geometry students. Welcome to your video lesson for lesson 3.2.3 and 3.2.4. Today we're going to talk more about similar triangles. We've spent some time over the past few lessons looking at shortcuts to prove triangles are similar. We looked at the angle-angle shortcut, which used the third angles theorem, and we looked at the side-angle-side similarity shortcut, which we will use in our first problem here. But today we're going to try to connect we're going to try to connect similar shapes to congruent shapes, which we've maybe talked about before. Congruent shapes are those that are the same shape and same size. And then we're also going to expand to one more similarity shortcut, which will give us 3 total. And then talk about, again, why one of them is not valid, okay? So the first problem in section 3.2.3 that we're going to look at is problem number 73, which gives us this picture over here of 2 triangles, triangle PDQ and triangle YZX. And our teammate or our classmate has asked us to prove that these 2 triangles are similar, okay? So we're going to try to explain why these 2 triangles are similar using flowchart proof and the side-angle-side similarity shortcut. Hope that you can notice in these 2 triangles we do not have 2 pairs of angles that are marked as congruent, but we do know that angle Q is the same as angle X. All right, so for today, to make my life a little bit easier, I am actually going to be drawing out my own little flowchart bubbles here. So the first thing that I would say that I know based on this picture, if I'm trying to prove the triangles are similar, it's important to note, I think, that angle Q is congruent to angle X. That's the proper notation there for that, angle Q congruent to angle X. That's in one of my flowchart bubbles here. Okay, angle Q is congruent to angle X. I also think we need to talk about the ratio of some corresponding side lengths, because remember, the sides in similar shapes are supposed to be proportional. So for example, if I look at the side DQ divided by the side ZX, those are corresponding sides in these triangles. That'd be this one here along with this one here. Hopefully you can notice that both of those are marked as 17 for me. So the ratio of those 2 side lengths is 1. Okay, so I know that. And then similarly, I know that PQ divided by YX, which would be the sides that are labeled 23 units, I can make a ratio of those as well. And hopefully what we notice is that the ratio of the corresponding side lengths in these 2 triangles is the same for those corresponding sides, right? So these sides are proportional, we say. Proportional, meaning they are equal ratios. So I can draw one of these and one of these, and I can just say that DQ over ZX is equal to PQ over YX, right? I can make this proportion right there. How can I make that proportion? How do I know those sides are proportional? Because proportional means equal ratios. So that'd be my reasoning for that one. And then because these 2 sides are proportional and angle Q and angle X are congruent, which is the side in between is the angle, in between those proportional sides, I think my flowchart then ends up right over here at another bubble, which I think says exactly what my friend would like. That triangle, again, that's my notation for a triangle, DQP is similar to triangle ZXY. ZXY. And again, we got to make sure we match up our letters, right? So D is with Z, P is with Y, and Q is with X, right? And how do I know that's true? I know that's true because of the side angle side similarity shortcut. Okay, so there is my flowchart proof of letter A here of number 73. Okay, so I made a flowchart proof that shows that picture. I have similar triangles. All right, so letter B, my classmate says these triangles are not just similar, they're congruent to each other. Now, it asks, is he correct, right? Are these two triangles over here congruent to each other, or are they just similar to each other? Remember, congruent means same size, same shape. Similar just means same shape, but not necessarily the same size. Are these shapes the same size? And certainly the answer is yes, because the 17s are equal and the 23s are equal, right? So they are, the side lengths are equal to each other. They're not just proportional, right? So what special value in your flow chart indicates that the triangles are congruent? That is right here. There's a 1 right there, and there's a 1 right there. And those ratios, right, of those two corresponding sides really tell me the zoom factor to get from one triangle to the other, right? What is the zoom factor here? The zoom factor is 1. But if I have two similar triangles that have a zoom factor of 1, well, then they're the same size, in addition to being the same shape, right? Because they're similar. So if they're the same shape because they're similar and they're the same size because the zoom factor is 1, then we would call those shapes congruent, okay? So it says write a conjecture in if-then form for your observation in part B. So my observation would be this. In part C here, it would say if similar triangles have a zoom factor of 1, zoom factor of 1, then, right, there's my then, if, then, well, then they are, oops, sorry, they are congruent. That's actually a pretty good definition for congruence. Sorry, I ran out of space there. Then they are congruent, okay? So this right here is because of the zoom factor of 1 makes the triangles the same shape because they're also similar, right? So notice in my hypothesis, they are similar triangles. I'm starting with that. And then if they have a zoom factor of 1, they must be congruent to each other, okay? Now that's for right now a conjecture. I'm not going to take time to prove that right now, okay? Because there's something else that we actually need to prove, which is a little bit more pressing for us, okay? So if we look at the next problem in our book, which is number 74, okay? It's the same classmate here, same classmate offering us a new challenge, and he wants us to look at the diagram he has here and see if we can find some similar triangles, see if we can prove some triangles are similar. All right, so he has this big triangle over here, triangle VTM, and he has drawn a line S to N right here. Right, there's our line S to N. It intersects the sides so that the subdivided lengths are proportional. What that means basically is here, if we have B divided by A, that's the same as D divided by C. Okay? He asked us this question. Is line VT, which is that side of his triangle, parallel to side SN? How do you know? The answer to that question is certainly yes, it is. That's another theorem that we essentially will be proving here, okay? The theorem would say if a line divides two sides of a triangle proportionally, then it is parallel to the third side. Okay. This I might call something like the proportional divider theorem, or something like that, if you want to give it a fancy name. Okay, the proportional divider theorem. If a line divides two sides of a triangle proportionally, then it must be parallel to the third side. Okay, and I can prove it to you by drawing these two triangles separately and trying to deal with their side lengths and use the side angle side similarity shortcut again to prove that they're similar. So let me do that here. I'm going to take this triangle here, and I'm going to call this one MSN. MSN Messenger. Anybody remember that? No, you're not from 2006. Sorry. Then what if I have VTM? VTM looks something like this. Slightly bigger version of the same thing. VTM. Now, I know that in this triangle here, MSN, I know that this side length is A and this side length is C. That's what they've shown me in this picture here, A and C. Now, the distance from M all the way to V, we need to be a little bit careful. Okay, the distance from M all the way to V is, I think, A plus B. And I think the distance all the way from M to T, hopefully you would agree with me, is C plus D, those two lengths put together. Okay. So now we have these two triangles and we have these side lengths. And what I'm going to try to do is I'm going to try to prove the triangles are similar by side angle side. Now, I'm not going to do a full flow chart for the sake of time, but I want to explain to you where I get the sides and where I get the angle from. Okay. So the sides should be fairly obvious. The ones that I'm going to try to show are proportional. The angle must be between them. So I want to talk first about angle M. Now, notice I said angle M just once because this angle M here, isn't it exactly the same angle M as this one? And I think this angle is certainly going to be the same measure as itself, right? Both of these triangles have an angle that's however many degrees that is. Maybe it's 40 or 30 or 42 or whatever it is. It's definitely the same in these two triangles, right? So that's my congruent angle here in the middle. Okay, so I got that. Now let's deal with the side lengths. I'm trying to show, right, that A plus B, which is this side, VM, divided by A, which is this side, right, SM, is equal to C plus D divided by C. Now, a little bit of algebra is going to let me do something to show that this is true, okay? When I have a numerator of a fraction, which is a sum of two things, I am perfectly allowed to split those two things over the same denominator. Okay, it's kind of like the opposite of adding together fractions with the same denominator, right? Common denominators would let me do A plus B over A. And then the same thing can happen here with C and D over C. So I want you to notice now that when I split these fractions up, which I'm allowed to do with the numerators only, by the way, not the denominators. If it's A plus B down there, you can't do it, but the top you can. A over A, isn't that just equal to 1? For sure. And then this says plus B over A. And then the other side says, well, C over C, isn't that also just 1? And then it says D over C. So notice that both sides have a plus 1 on them, right? So can I minus 1 on both sides? A little bit more algebra. Scribble those out and scribble those out. What are you left with? B over A is equal to D over C. Now, do you guys remember how we started this proof? We started with he drew the line so that the subdivided lengths were proportional. That means B over A is equal to D over C. So we know this is true, right? We know that's true, which means this also must be true, right? So those two things are both true, but this is my proportional sides. So now what do I know about this triangle and this triangle? They are similar by side angle side. All right. Now, I'm almost done answering his question. What was his original question? Is VT parallel to SN? So is this line parallel to this line? Well, hopefully I've convinced you that the triangles are similar. And the similar triangles actually give me a whole bunch more information, because what do we know about similar triangles or similar shapes in general, particularly about their angles? Don't we know that their angles have to be congruent to keep the same shape? Well, that would mean that angle V right here at angle V has to be the same as at angle S, because those would be the corresponding angles here, right? These two guys, V and S, have to be the same number of degrees in those two similar triangles. But again, go back and examine this picture, right? Let's focus our attention on this picture now. Angle V and angle S. Not only are they corresponding angles in the triangles, but aren't they also corresponding angles with this line and a transversal? Sure. Well, what do we know about the lines that a transversal crosses over if the corresponding angles are the same number of degrees? What do we know about the lines? They have to be parallel, right? That's the converse of the corresponding angles theorem. So because the triangles are similar, then the angles are congruent, and then I know the sides are parallel, right? So those lines are parallel. SN and VT, parallel lines, yes. Now, hopefully you understand that that proof would be a relatively large flowchart. There was a lot of stuff going on, particularly, remember I did some algebra, I did some M is congruent to M, I did some corresponding angles theorem, right? That would have been a big flowchart. So this is maybe our first example of a proof that it might be actually easier to see the flowchart version, and I may do that for you when we get back in class. But for now, we'll just understand that this is true. If you draw a line so that it divides the sides of the triangles proportionally, then they must be parallel lines, okay? And the converse is actually true as well. Now, I want you to take a quick pause, just take a break for like 2 minutes, stand up and go get yourself a glass of water, come on back, and we're gonna keep going. But I want you to take a little break here. This would be like part 1 of class, okay? We're on break now, we're gonna part 2. So pause and take 5 minutes and then come back. All right, now that we're back, we have one more similarity shortcut that we want to write down in our notes, okay? So we previously had the angle-angle similarity shortcut, and we had the side-angle-side similarity shortcut, okay? And today we're adding side-side-side similarity shortcut. This is a situation where we don't actually know anything at all about the angles, at least in the beginning, right? But we're going to try to, well, we do know enough about the triangles as long as all the corresponding sides are proportional that we don't have to worry about the angles. And I can prove that to you using a little demonstration down here. So again, write down that similarity shortcut and then let's prove it so we can use it moving forward. So I have these two triangles here, okay, ABC and DEF, ABC and DEF. And we know that the sides are all proportional, okay? So AB divided by DE, this one divided by this one, is the same as BC divided by EF, which is the same as AC divided by DE. We know all of those are the same proportion. So that's done. We just, if we want to prove they're similar triangles, we would need to show all the angles are the same, right? Okay, so here's how I'm going to do that. What I'm going to do is I'm going to draw myself a little line in the big triangle, okay, in the big triangle, so that this length from D to P, is equal to AB. So, okay, so those two sides are the same. AB and DP, AC and DQ, okay? Yeah. So we draw that line, okay, so that this is the same as this is the same as this, right? Now, what I want to convince you of, though, is that that has just shown that the line I drew has to be parallel to EF, right? It has to be parallel to EF based on what I just did before we took a little break. Because if I know that AB divided by DE right here is the same as, say, CA divided by FD. I'll skip over to this one. Can't I replace AB now with DP? DP over DE? DE. And can't I replace CA with DQ? DQ over FD? Those also have to be proportional, right? Again, I've subbed out this AB for DP because I drew my line so that they're the same, right? Down here, DP is the same as AB, DQ is the same as AC. So I swapped those out, but now look at what I've done. DP over DE is the same as DQ over DF. Yeah? But that's exactly what I just had before. That now this is proportional to this, right? This guy down here, and this is proportional to QF. And if I draw a line that divides the side lengths of the triangle so that I have proportions like this, then this side is the same as that side, right? Or sorry, not the same, but parallel. And what did parallel lines give me up above? Well, parallel lines, I used corresponding angles to prove lines are parallel, right? But I can go the other way as well. If I know these lines are parallel, that should convince you that angle Q is congruent to angle F. It should also convince you that angle P is congruent to angle E, right? And if I have two angles congruent in two different triangles, then the third angle must be congruent. And it's also extra obvious in this picture because angle D is the third angle for both, right? So angle D is congruent to angle D, right? But remember that this triangle DPQ, I drew the line so that it was the same as this triangle ABC, right? I made sure that that was the case. So now this triangle is congruent to this triangle, which means all of these D's, P's, and Q's here, I can replace with C's, right? Angle C and angle B and angle A. Okay. So again, that's a proof that just starting with the same sides, right, proportional sides, I can get myself to this, which is that all of the angles in these two triangles have to be the same. They have to be. So side, side, side is a wonderful, wonderful shortcut for similarity if you don't know anything about the angles in the picture. You don't need to. All right. Now, we have one final question to deal with, and hopefully it's relatively straightforward. It's something we touched on in class on Friday, I believe. I wrote kind of a naughty word on the board, and we talked about how that was not an okay way to prove that triangles are similar, right? So I'm going to show you why that is right now in this case, using this picture right here, okay? So using this picture, it says, Corey's team has put side-side angle similarity on the list of possible triangle similarity conditions. Testing their idea, they started by drawing this triangle, okay? 4, 5, and 49 degrees. That's this side length, this side length, this angle. The question is, can we make another triangle with a 4-centimeter side, a 5-centimeter side, and a 49-degree angle that we know for sure is not similar to this one? Because if we can, that would disprove this whole side-side angle thing. Now, hopefully you can see if you reversed side-side angle and you went angle, side, side again, we would have kind of that naughty word that we talked about on Friday, right? So that's my goal, is to try to make another triangle with these same 3 pieces of information that I can prove, or convince you anyway, is not similar to this one. And it's not actually that hard to do it. What I need you guys to think about is kind of like a pendulum, okay? A pendulum that swings, like an arm that's anchored somewhere, and we can swing it around, okay? That doesn't change how long it is, just kind of changes the angle, swings around. And I want to do that by making the point between the 4 and the 5 here a hinge, like a that's my hinge point, okay? You can't move that point right there. But I am going to allow myself to move this point up here. Okay, so I'm going to move this point which changes this angle. But remember, I don't know how many degrees this angle is, so it doesn't really matter how many degrees it is. Could be 50, could be 150, could be 5, right? Doesn't matter. As long as this stays 4, this stays 5, and I don't touch this angle over here. So if I were to move this, and I were to like swing it down and make the angle smaller, the 4 centimeter side would do something like this, okay? It would like kind of make this little loop like this, and then it would impact again right there. It would impact this side of the triangle here and here. So I can make a 4 centimeter side right there in addition to the one up here by just kind of swinging the pendulum like this, all right? And I'll show you a physical example of this in class. But what that can show is that now I have this triangle. I have a 5 centimeter side, I have a 4 centimeter side, and then I have here still a 49-degree angle. So 49 degrees, 4 centimeters, and 5 centimeters. Okay, 4 centimeters and 5 centimeters. But what that should convince you of, I hope, is that these two triangles that I drew are certainly not similar to each other. I know it because look at this angle here, which maybe I'll do in blue. If you focus on this blue angle up here, okay, this one, that has to be bigger than 90 degrees. At least in my picture, it is bigger than 90 degrees. It's an obtuse angle, okay? But over here, this is an acute angle. So this is acute. He's cute. And this is obtuse, okay? Cute and obtuse. Cute and obtuse. So they cannot be similar triangles, but both have a 49-degree angle, both have a 5 centimeter side and a 4 centimeter side, right? But that angle is not between the two sides, which wrecks the whole thing. So side-side angle or angle side-side, donkey butt word, is not an okay similarity shortcut. Okay, so please do not ever write SSA on a geometry test or homework or anything like that. Okay, so again, if we're going to list our valid and okay shortcuts, the easiest one, if you know the angles, is angle-angle similarity. If you know one of the angles and two of the sides on either side of it, right, where the angle's in between, like that hinge, that's fine too. Or if you know all 3 sides, that's also fine to prove that the triangles are similar. Again, sides here are proportional, right? Equal ratios, angles congruent, all right? So those are your 3. Make sure those are in your notes. And that's going to be all I got for you today. Thanks for bearing with me and hanging in there with me. And we will see you very, very soon.